Okay, right. So the theorem statement from last time was that we went through very quickly was the following. Right? It said that suppose so over the field of C, right, we're going to consider the statement was that every operator has an upper triangular matrix. Right, this is what the statement was. So let's go through the statement again. So here, suppose V is some finite dimensional complex vector space, right, and T is some linear operator on V, right? Then T has Harshi, can you keep yourself unmuted the entire time, because then it's a little bit easier for me to keep track of whether things are making sense. Sorry, yeah, it just helps me. Is the T has an upper triangular matrix with respect to some basis of V. Okay, is the statement okay?
Yes, sir.
Yeah, okay. So how are we going to prove this? So we're going to do it by induction, right? So we're going to do induction on the dimension of the vector space V. So clearly the result holds if the dimension of V is 1, right? Because then it's just a one-dimensional, so there's just some number A, that's the entire matrix, and this is upper triangular because there's nothing below the diagonal, right, to impose conditions on, right? So this is fine?
Yes, sir.
Okay. And right, so now suppose that the dimension of V is strictly greater than 1, okay? And the desired result holds for all complex vector spaces whose dimension is strictly less than the dimension of V. Okay, so if dimension of V is n, we are going to assume that the result holds for all matrices of dimension n minus 1. Sorry, all vector spaces of dimension n minus 1. Is that okay?
Yes.
If something is not clear, just say okay. Don't hesitate, please. Okay, so now let lambda be any eigenvalue of T. Okay, and we know that for a complex operator, there is always at least one eigenvalue. Complex operator meaning an operator in the complex where the field is the complex numbers, right? So this we already proved in theorem 5.21. Is that okay?
Yes.
Okay. Right. So now let us define U. And so, okay, so now it will become a little bit heavy on the notation. So let's go a little bit slow. So let U be the range of this operator T minus lambda I. So lambda, remember, is one of the eigenvalues of this operator T. We are considering an operator T minus lambda I, and we're looking at the range of this operator, right? And that is what we're defining U to be. So U is defined to be range of T minus lambda I. Is that fine? Is the definition okay?
Yes, sir.
Right. So now the question is T minus lambda I surjective or not? Okay, so surjective, remember, is just 1-to-1, right? So we are asking, is T minus lambda I surjective? What do you think? Harshi, what do you think?
So I don't think, because like from, if I don't know if it's correct or not, like initially
It's
we
okay.
proved that null space of T minus lambda is 1, so it cannot be 1 1, and so
Precisely.
it cannot be such.
Exactly. So here the point is that we have at least one vector, right? So this is exactly the argument you're saying, right? So we have at least one vector such that TV gives you lambda V, right? That is what it means to be an eigenvalue of T, correct? And V is non-zero.
Yes.
And then exactly this is what you're saying, that there is at least one eigenvector which is non-zero, right? So V is non-zero and it is in the null space. Okay. So if the null space has a non-zero vector, that means that the map cannot be 1-to-1. Okay, so this we've proved many times. You can also see it from rank nullity. Okay, so we know that it's not 1-to-1. And what does that mean? Then we can apply rank nullity and conclude that the dimension of U has to be strictly smaller than the dimension of V. Right? Is that okay?
Yes, sir.
Right? Okay, so this is very nice, because now we already know that our theorem statement, sorry, the what we wanted to prove, right, already holds for n minus 1 dimensions, right? So this is nice. So now let's continue the analysis. The theorem claims, the proof claims that U is invariant under T. Okay, so U is a set of vectors. It's a subspace, right? Because it's the range of some linear operator. The claim is that this subspace is invariant under T. Okay, so let's see how we prove this. Is the claim okay? Is the statement of the claim okay? Okay. So let's see how to prove this. So suppose that U is in the subspace itself. So little u is in the subspace capital U. Okay. Then little t acting on U would be the same as T minus lambda I. This is just the definition U plus lambda U. So all I've done is I've added and subtracted lambda identity. So this statement okay?
Yes, sir.
Okay. And now what we are going to do is we know that this part, this first vector, right, this belongs to U. Right? Why?
Because he was invariant.
No, we have to prove that U is invariant. So what was the definition of U, right? So the definition of U was, it was defined to be the range of T minus lambda identity, right? Here the
Yes.
definition of U is that it is just the range of lambda minus identity, right? You see that?
Yes, sir.
And range basically means what? It means that any vector, if you apply the linear operator on it, whatever result you get is going to be in the range, right?
Yes, sir.
So that is why, so if you apply U on this vector, it will be in the range of that vector, correct? Or in the
Yes,
range
sir.
of that vector. Sorry. Is that okay? Does it make sense?
Yes, sir.
Okay, fantastic. All right. And then obviously this vector itself is in U, right? Because it's just a scalar multiple. It's a scaling of the vector U itself, correct? So this thing belongs to capital U as well. Is that okay? Is that okay for both of these, term 1 and term 2?
Yes, sir.
All right. So what do we conclude? We conclude that TU therefore belongs to capital U, right? Because it's a linear combination of vectors in capital U. So that will also be a vector in capital U because capital U is a subspace,
Yes, sir.
right? Okay.
Sir, here lambda times u belongs to u is just because of the property of it being scalar multiple, right?
Exactly. So
Okay.
since U is in the vector space, any scalar multiple is also in the vector space. Exactly. Is that okay?
Yes, sir.
Okay, perfect. Very nice. Okay, and therefore we have that T restricted to U is an operator on U. Okay, so sorry. So this basically concludes, what did we want to first conclude? That U is an invariant subspace of T. This we just established, right? We showed that if you have T acting on U, the resulting vector will also be in U. So therefore, T leaves the subspace U invariant. Is that okay?
Yes, sir.
Sure, you don't sound very confident. You
No,
can
sir.
wait a
I
few
am.
seconds.
No,
Okay,
it's fine.
all right. And then this T given U is an operator on U. This is well defined now, right? Because we saw that we can restrict the a linear operator to an invariant subspace, and that thing is also an operator. Right? This we saw last time. Yeah.
Yes, sir.
Okay. And here's just some notation. I am going to be a little bit sloppy, and I might write T given U as not given, whatever, restricted to U as T subscript U, but that's okay. All right. So now let's write the rest of the argument. So this part is maybe a little bit more delicate. So let's do it a little bit little more carefully. Okay. Right. So now what we're trying to argue is that using our induction hypothesis, we know that there is some basis U1 to UM of capital U. Excuse me. Of capital U, with respect to which TU has an upper triangular matrix. Okay. So why that is because U is n minus one dimensional, right? right? Because we showed that the kernel is non-zero, then we invoke rank nullity to conclude that U is n-1 dimensional, right? And then we are, so if we restrict to this this linear operator, if it's restricted to this subspace U, then we can apply the induction hypothesis, right? Which was that any n-1 dimensional subspace has an upper triangular form relative to some basis, correct?
Yes.
Okay, so we denote this U1 to UM. We denote this basis by U1 to UM. Okay. All right. Now it says for
So
each,
is M equal to n-1?
yeah, here we can take M equal to n-1. Yeah. I think so. Okay, unless I'm missing something, it should be n-1. Actually, maybe not. No, you're okay. Okay, no. If the eigenvalues are distinct, are we assuming distinct eigenvalues? No, we are not. Okay, no. It may not be. It may be less than. Okay, so M will be at most n-1. Let's put it that way. You're right. Thank you. Thank you for pointing that out. Okay, so dimension of U is at most. The reason is that you could have had. So here I said that there's at least one vector, right? But there could be two vectors with the same eigenvalue potentially. So there's TV equals lambda V. You could also have TV prime equals lambda V prime, right? So then the kernel will have two elements, and then you would have the dimension getting smaller. Okay, that is a good question. Is it okay? Yeah, it is at most n-1. So little m cannot be more than n-1.
Okay.
Okay. But nonetheless, our reasoning still applies, right? Because we assume that the induction hypothesis applies to all vectors with dimension at most n-1. Okay, so thus we have that for each j using proposition 5.26. So proposition 5.26 says that here are the conditions for something to be an upper triangular matrix. Okay, so a matrix is upper triangular with respect to some basis is equivalent to saying that when you take the linear operator T, okay, so there's V1, V2 all the way to Vn. Okay, this is the basis. So if you apply it on the jth basis, okay, the result has to be in the span of V1 all the way to Vj. It cannot go outside of this. Okay, so in particular, it would mean T1 is in the span of V1, TV2 is in the span of V1, V2, okay, and TV3 is in the span of V1, V2, and V3, right? And so on. Is that okay? Is the statement clear?
Yes.
Already. And also, you don't have to say sir, okay? You can just say yes. It just feels a bit odd. Okay, and then the other thing is that, of course, you can say T. Okay, no, sorry. The other thing is that this span is invariant under T. Okay, so span of V1 to Vj. When you apply T, okay, this will give you the same thing. The span doesn't change. Okay, so this is condition B. This is condition C. So what is being said by the proposition says that these three things are equivalent, whether the matrix has an upper triangular form, whether the conditions in B are satisfied, or whether the conditions in C are satisfied. Is the proposition clear?
Yes.
Okay, very well. So now we can continue. So here we are saying that because we know that our operator T restricted to U has an upper triangular form, using proposition 5.26, we can conclude that T acting on Uj, which would be T restricted to U acting on Uj, is inside the span of U1 to Uj. Is that okay?
Can you repeat this part?
Yes, for sure. Okay, so T acting on Uj, right, is the same as T restricted to U acting on Uj. Remember, because we could write T. So restriction of T on U is basically looking at the linear operator. So normally T goes from V to V, right? T restricted to
Yes.
U from U to U. My U's and V's look similar, so I'll make it a little bit. Okay. Because remember, U is an invariant subspace, right? So all vectors in U are mapped to U.
Yeah.
So since we are only applying it on Uj belongs to U, right? It's a
Yes.
basis vector space. Therefore, we can restrict this opacity to acting on Uj. And so that's all this first statement is saying. This one is
Okay.
just a question of notation mostly. Is that okay? Is the first step okay?
Yes.
Okay. And then the second step is following from, so if you look at point B in the proposition, proposition, I'm saying, in the proposition, right? Point B here, it tells you why the second point should be true, right? Because we assume that T given U, not assume, we concluded that T given U has an upper triangular form, right? Using the induction hypothesis. Therefore, T restricted to U acting on Uj has to be inside the span of U1 to Uj using exactly this condition. Right? We're just using U's instead of V's here. And we're using T restricted to U instead of V's. Is that okay?
Yes.
Okay, good. All right. So now what it's saying is, suppose we do this, right? So now what we're going to do is we're going to extend U1 to UM to a basis. So you have U1 to UM, this you already had, and you added a bunch of more elements, V1 to Vn of V. I think it should be K. Let's make it K because the sum has to add up. Okay, sorry. So you had U1 to UM elements, you're adding a few more elements so that you get a basis for capital V. Remember, U was a subspace of V, right? So you can always
Yes, sir.
extend the basis to get a basis for capital. Is that okay?
Yes.
All right. Now, for each K, we have that T acting on VK. Okay. Again, we can just add and subtract lambda times identity and write it as follows. Okay, so for each K, we're going to write TVK equals T minus lambda IVK plus lambda VK. Is that okay?
Yes. So
All right, brilliant. And we also note that T minus lambda IVK has to be in U.
yeah, we showed it earlier.
Exactly, right? So for any vector that acts on T minus lambda I has to be in U because U was defined to be the range of T minus lambda itself, right? So therefore, this is always going to be true. So far you're with me, right? Everything makes sense? So we have
Yes.
that U can be written like this, and we have that the statement is true, T minus lambda. Okay. So now what's the conclusion? So the conclusion is that for each K, it holds that TVK is inside the span of U1 to UM and V1 to VK. Okay, so let's see why that is. So we have TVK, right, over here. So we're going to look at this part. So TVK, this part we just showed belongs to U, right, using this NB, correct?
Yes, sir.
And we already argued that, okay, sorry, and this part is going to be inside, it's just going to be inside the span of VK, right? It's a single vector, it's just a scalar. Correct? So what we're guaranteed is that TVK is going to be in the span of U1 to UM because, this is the same as span of U1 to UM, right? And the span of VK. So we can actually add a few more vectors. It doesn't change anything. Is that okay? I'll give you a second just to make sure that it's okay.
So basically we showed that T minus lambda I that belongs to U, which is span of U because it's a range.
Yes.
And the second part belongs to span of VK.
Yes. Yes.
What exactly are we trying to show about T of VK?
We're trying to show that it belongs in the span of these this entire
Okay,
vector
okay.
space.
Oh, got it.
Yeah. right? So T of Vk will be in this span. That is what we're trying to show. And this is kind of straightforward, right? So you can forget this part for now. Okay, so this we call 5.29. So this is equation 5.29. 5.28 we already established, assuming that Tu is a vector. Sorry, is a the T restricted to U is already an upper triangular matrix, right? So using the proposition, we already had 5.28. Okay, so now what do we have? We have both 5.28 and 5.29, which basically satisfies condition B here for the entire basis of V, right? So V was written as what? It was written as U1 to UM, right? Comma V1 to VK, right? And basically for each vector here, we are able to show that when T acts on UI, it would be in the span U1 to UI, right? And if T acts on VJ, it would be in the span of U1 to UM and then V1 to VJ, right? So this is the condition that we would need if we wanted to show T is upper triangular, right? Using exactly the same proposition, but T is upper triangular. Is that okay? Wait, what was your name? I forgot. Harshi,
Yes,
is it? It's not clear, huh? Okay, okay. So let's state it again. So this proposition, okay.
so it's clear. It's fine.
Oh, it's clear. Sorry, the audio was a little muffled. Okay, right. So then, using this combination, we can conclude using proposition 5.26 that T has an upper triangular matrix relative to this basis. Yeah.
Yes.
Okay, fantastic. So this is what we wanted to prove that we couldn't do very well last time. There's another proof that we can skip for now. I think that's all right. Okay, so then we can continue. Maybe we can ask someone else to volunteer now. Let's see. Who was the second person? Yeah, thank you so much, Hershey. This was helpful. Then there's, I guess, Emmanuel. He's around. Yeah. Okay.
Good morning, Professor. Good afternoon.
Hey. Sorry, could you say that again? I didn't catch that.
Good afternoon. Can you hear me?
Yes. Good afternoon. How are you doing?
Yeah, pretty well.
Okay. So great. So let's continue then. So proposition 5.30 says the following. Wait, let me actually say the story part. Okay, so can we say something about the operator being invertible given its matrix? Okay, so far we looked at the that whether a linear operator has an upper triangular form or not, right? So we had some characterization. Now we're asking about invertibility of the matrix. We already saw it in Hoffman and Kunz, but that was in a slightly different context, right? It was using row matrices and so on. And now we're going to look at, I guess, using this upper triangular matrix and things like that. So the proposition is the following. So it says determination of invertibility from an upper triangular matrix. That's sort of the title I sort of forgot to put it in brackets. The statement is as follows. It says, suppose T is a linear operator V that has an upper triangular matrix with respect to some basis V. Okay, so we have some upper triangular matrix. Then T is invertible if and only if all the entries on the diagonal of that upper triangular matrix are 0. Okay. So basically the diagonal has to be non-zero. Diagonal entries have to be non-zero, assuming it's already in an upper triangular form. Is the statement okay?
Yeah, that's fair.
Okay. So let's see. So if the matrix is upper triangular, we want to argue that it is invertible. Right. So suppose V1 to Vn is a basis of capital V with respect to which capital T has an upper triangular matrix of this form. So this is fine. So it's just the basis with respect to which we have this. M is the matrix for the operator. Right. This is the notation the book is using. Matrix for T. Okay, so now we need to show that T is invertible if and only if all the lambda i's are 0. So it does it at once. No. Okay, sorry. All right, so let's see then. So first, suppose that the diagonal entries lambda 1 to lambda n are non-zero, are all non-zero. Okay, so suppose this is the case, that they're all non-zero. Then this upper triangular matrix 5.31 implies that T v1 obviously is lambda v1. This is just immediate from the definition itself.
Yeah.
Right, because
Yeah.
so remember the, yeah, exactly. So let me just write it down in case others have forgotten that if you have say 1 0 0, right, you're going to basically pick the first column as the answer because it'll be lambda 1 0 0 and so on. Okay, so whichever entry is non-zero, you will pick that column. So here it's kind of completely immediate, right? The TV1 would give you lambda 1 v1, so this is fine. Since lambda 1 is not equal to 0, we have that T of v1 by lambda is v1, and therefore v1 is in the range of T. So that is fine.
This is yeah.
So v1 is in the range of T. Okay. Now, capital T acting on v2 by lambda, right? This can be written as a v1 plus v2 for some scalar a. So why is that? So let's take a look. v2 by lambda 2. Okay. This is going to do what? It's going to suppose this number is b. Okay. So when I write lambda 1, yeah, let me use a different column. So now if I multiply it with 0 1 0 zeros, I will get b lambda 2.
Select this. Yeah.
Exactly. You just select the second column, right? And now this I can obviously write as b. So b times 1 0 0, right, plus 0
Right.
and 0 0 times lambda 2, right? And of course, if I had initially multiplied the whole thing by 1 by lambda 2, right, I would have 1 by lambda 2.
Yes.
Lambda 2.
Okay.
This thing should be 1.
That makes
right?
sense.
Right. So you should get something like AV1. So this is V1, right? This is V2. And this should give you
So here the A would be like the entry above lambda 2 divided by lambda 1.
Exactly.
Right.
Precisely. Right. All right. So this is fine. And then it says what? It says that the left side. Yeah. Tell me.
So can you explain that part again? AV1 plus V2. Don't understand.
Yeah, for sure. So let's do it again. So here, what we are saying is that let's look at this matrix again. Okay. So lambda. So what did we want to show? Right. So we want to show that T v2 by lambda 2 would give you a v1 plus v2. This is what we want to prove. Okay. Given that the matrix has an upper triangular form. So let's write down the upper triangular form a little more explicitly. T. So suppose you have a 3x3 matrix. Okay. Just to be concrete for now. And you multiply it by 0 1 0. Right. So remember v1 is just going to be 1 0 0 here, right? Because we are writing it in the basis of v1 to v, right? Since you're writing in basis, we can write it as, right? Okay. All right. So this is basically v2. So I'm multiplying. I'm computing t v2. This is what I'm computing. So when we compute t v2, what do we get? We get that the second column here, right, is what we will pick. Right, that's what matrix multiplication does. So as an answer, we'll get b lambda 2 and 0. Is that okay?
Yes, got it.
Right. And then the rest is kind of straightforward, right? So this I can write as b 0 0. Actually, let me just write it directly. So I can write it as b times v1, right, plus lambda 2 times v2. Right? Is that okay?
Yes.
I've just expanded. And then, okay, so we have this. So this, what I computed now is TV2 is the same as BV1 plus lambda 2 V2, right? But I can divide everything by lambda 2, right? So I can just write it as V2 by lambda 2. It's just a scalar. be p by lambda 2 v1 plus v2, right?
Yes.
Okay, and then this is the part that would be a. That we were
Okay,
saying it's
sir,
some.
got it.
Yeah, that's okay. Perfect. Any other questions? Is it okay for everyone else? Yeah, it's very good. Thank you for asking. Okay, that it encourages others also to ask in case something isn't clear. All right. So this is okay, and then so we can write this equation. We had this equation to begin with. Okay, and then let's see what the argument says. It says the left-hand side of the equation above and AV1 are both in the range of t.
Yeah.
Saying that the left-hand side here is in the range of t.
All
The
right.
left-hand side of the equation above and
Yeah.
AV1. AV1 is also in the range of t.
From the previous set of
Why?
statements. Yeah.
Because of this guy, right?
Yeah.
Right? Are both in the range of t. Thus, the linear combination, that is V2, right? So you take a linear combination of an object in the range, which is on the left, and this object. So basically, it's just saying you can write V2 as V2 minus lambda minus AV1, right? We can do that.
Yeah.
And both of these objects are in the range of t. Range of t. Therefore, V2 also has to be in the range of t. Is that okay? Because
All
it's a
right.
subspace. Range of t is a subspace,
Yeah.
so therefore linear combination. Okay, so one can proceed similarly and compute V3 by lambda 3, and then you'll obtain BV1 plus CV2 and plus V3. And then again, the left-hand side of this equation, and so this left-hand side is again in range of t. Right, and this we proved above is in the range of t. Oh no, sorry. Which one did we prove? We proved this guy.
T1
V2
and
is
T2. Yeah.
of t, right? And we proved this is also in the range of t. Right,
So
so
the result
CV is coming from this step, and V1 is coming from the previous step, right? The one we did here. Okay. So
right.
then we conclude
Yeah.
that V3 is also in the range of t, right? Okay. So one can continue this way and conclude that V1 to Vn, all the vectors are in the range of t. So that is fine. Yeah.
Yeah. Yeah.
All right. And then since V1 to Vn is a basis for the vector space V, right? We already know
Yeah.
this, right? Because
Yeah.
it's
From the beginning. From the premise. From the premise. Yeah.
From the premise, exactly. So it follows that range of t is actually the same as V, because you have n linearly independent vectors, and
Yeah. Just that.
so that basically gives you the entire vector space. Okay. All right. So once you have this, so once you know that the range of t actually matches the vector space you're in, you conclude that t is surjective. Because otherwise, there are many ways of saying that, but
yeah, that's the definition. Range t equals domain. Or yeah.
You're right. Yeah, that is just exactly the definition. You're right. So this is just the definition of surjective. Yeah. Yeah, I think I was thinking it's injective, but yeah, that is also the case. But yeah, we don't need that here. So T is surjective, right? So domain is the range matches the codomain, and so that it in turn means that T is invertible, right? And this I think we proved already, because whether you're
and all that.
surjective, injective, or invertible, they're all the same, right? So this we sort of already showed. Or you can use rank nullity as well if you want to. I think that's how they prove it in the text. There are many ways of doing it. Now you're experts. So this is good. Okay. Right. So okay. So we have. So basically, the proof strategy here was just that we showed that you're spanning the entire range. We showed that T is surjective by using the upper triangular form. And then from that, we invoked the fact that an operator being surjective is the same as it being invertible. Okay, so this direction is fine. Now we want to do it the other way, right? We want to say that if it is invertible, then one can write it as an upper triangular matrix. Okay, so for this direction, we start with, of course, assuming it is invertible. And that in particular means that there is a non-zero eigenvalue lambda 1. Otherwise, t v1 would give you 0, and then you have two vectors mapping to 0, the 0 vector and a non-zero vector, so you cannot invert it. It's not 1 1.
Yeah.
Okay, so we assume that the first eigenvalue is non-zero, and then suppose that for some index j, it so happens that lambda j is 0. Okay, so actually I shouldn't say eigenvalue. I think I sort of messed up. What I meant by lambda 1 here is the lambda 1 here, the first entry of the matrix, because we're assuming it is invertible, and we're looking at the first. Wait, what is this?
Yeah.
I'm a bit confused now. Suppose T is invertible. What does lambda 1 even mean? He hasn't defined lambda 1. Okay, so I guess for now, let's just define lambda 1 to be the top left entry. Okay, we don't know about anything.
Okay, no. The text says that lambda 1 must be 0. Otherwise, we would have TV1 equals 0. And I think he means that lambda 1 is the first entry in like the matrix over there, like in that position.
Right. Yeah, so okay, yeah. So let's just take lambda 1 to be the first entry, right? That is probably going to be enough. Is that right?
Yeah.
Okay, so let's take let's take an arbitrary matrix and suppose lambda 1 is the first entry. Now,
I mean, we know. Okay, no, wait.
that doesn't make sense, right? Okay.
No, we're not proving upper triangularity. We're proving that all the entries on the diagonal are non-zero. So we have an upper triangular matrix. Is that the definition?
Yeah, let's see. Okay. So suppose T has an upper triangular matrix. Yeah, you're right. I think I wrote the thing wrong. You're right. So it's saying T is an upper triangular matrix, and we are trying to make statements about the diagonal entries. Okay, good. Yeah,
Yes.
good. Yeah, thank you for that. Yeah, so let me correct this. So T is diagonal entries
Are non-zero.
Yeah, non-zero. Yeah, I wrote this incorrectly. Yeah, thanks.
T is upper triangular is the premise, and that just means that the entries below the diagonal are 0. It says nothing about any of the entries on the diagonal or anything above the diagonal. So that's why it's not trivial.
Exactly. Yeah. So right. So the first step is that lambda 1 cannot be 0, and that is because when you multiply with the one vector, right, you'll get 0 times one vector, basically lambda times that vector, right? And of course, if this is 0, then you're clearly not invertible because two vectors are mapping to 0, so you cannot invert it. Okay, and then it's saying suppose that there is a non-zero entry at some arbitrary point later. So suppose for some j there is a 0 lambda. Then it says in this matrix 5.31, it follows that T maps the span of V1 to Vj into V1 to Vj minus 1. Okay, so that is basically kind of easy to see because so you have, suppose lambda j is the entry, right? That was non-zero. So you would have a bunch of, so let's call them, say, phi1, phi2, all the way to phi j minus 1. I shouldn't call them phi. Let's call them A. Maybe that's easier. Okay, and then when you multiply it with the vector which is all zeros except at the jth location, right, which is what I guess we were calling epsilon j in the previous book, right, you're going to get something which is a linear combination of vectors. So this would be in the span of V1
the non-zero. I mean, we would have at least one of A1 to AJ minus 1 is non-zero, but AJ would be 0. So it would be just as equivalent. Yeah, okay.
Yeah. Right. So here, so this, when we write it out, right? So when we multiply, so let me write it out more explicitly. So this T acting on epsilon j, right, would give you a vector which would be A1 times V1 plus A2 times V2 all the way to AJ minus 1, VJ minus 1 plus lambda j Vj, right? And this entire object is clearly in this span of V1 to So it is in the span v1 to vj, right? But the point is that we know that lambda j is 0, right? Because we were arguing in that case. So if lambda j were 0, then you're in the span of v1 to vj minus 1.
minus
Yeah, just to make the last one. Okay. All right. So this is fine. Now, since the dimension of span of v1 to vj is j, right, the j vectors, and dimension of span of v1 to vj minus 1 is j minus 1, because remember, these are basis vectors. So it follows that t restricted to v1 to vj is not injective.
Okay. This makes sense.
So
Yeah,
it says this
sense.
is injective by proposition 3.23. So 3.23 is saying that let V and W be finite dimensional vector spaces such that dimension of V is greater than the direction of W. Then no linear map from V to W is injective. Right? Because you're making the space smaller. So you have to have two things go to one. Otherwise, you couldn't make that happen. Right? So you say it cannot be injective. Okay. And so if it's not injective, what that means is there exists a vector v in the span of v1 to vj such that the vector is non-zero, and nonetheless tv is 0.
Yeah.
Right?
Not injective,
because
so null space is in 0.
Exactly. So the null space is 0. That in turn means that t is not injective, and thus it is not invertible.
Okay.
Okay. But this contradicts our assumption that t is invertible. So the argument basically saying that the moment you have any non-zero eigenvalue, you're going to be able to show that it's mapping something, a bigger space into a smaller space. And the moment that happens, you'll have a non-zero kernel, which would make it non-invertible.
Yeah.
Okay. So therefore,
This
it must be that our assumption is false, and therefore lambda j is non-zero. Okay. Any other questions for anybody else who's following? Emmanuel tends to be a bit quicker as well, I know, but anybody? Is this part okay? Right.
Yes.
Okay, fantastic. So this was proposition 5.3, right? It was saying that if you're given an upper triangular matrix, then being invertible is equivalent to checking that all the diagonal entries are non-zero. Right. Okay, thank you, Emmanuel. Let's see who. I think Mohan, is it the next person, or Manan? I forget. Manan. I don't think we have a Mohan, do we? Probably not. It's 135 or 150 strong class, so maybe. All right, Manan, are you around? We don't hear him. Manan, can you hear us? Okay. Samyak? Is it Samyak or Sanyak? My handwriting is so bad.
Yeah, sir, it's Samyak.
Hey. Okay. So is it okay? Would you help me for the next proposition?
Yeah, sure.
Thank you so much. Yeah, maybe in the meantime, someone can check what happened to Manan. I hope he's okay. Tends to be. Yeah. Okay. So let's continue then. It says, unfortunately, no method exists for exactly computing eigenvalues of an operator from its matrix. However, if we are fortunate enough to find a basis with respect to which the matrix is upper triangular, then the problem of computing the eigenvalues becomes trivial, as the following proposition shows. Okay. There are numerical techniques for finding good approximations to eigenvalues from its matrix. So we are going to basically assume that you have an upper triangular matrix and then try to see what we can say about the eigenvalues. Okay, in general, this problem seems to be difficult. We don't have an exact method for computing eigenvalues just from the matrix directly. And there are numerical methods, right? I guess this is pretty self-explanatory. Samyak, is that okay?
Yes, sir.
Okay, perfect. Yeah, you can keep yourself unmuted if you're not muting yourself anyway. Okay, fantastic. Yeah. Right. So let's start with proposition 5.32. It says suppose T has an upper triangular matrix with respect to some basis of V, then the eigenvalues of T are precisely the entries on the diagonal of that upper triangular matrix. Isn't that interesting? So if you have a matrix, right, and it's upper triangular, then even if you have extra non-zero entries over here, you can conclude that the eigenvalues are essentially the entries along the diagonal. It's not obvious, right? Because you could be applying T on some, say, if I apply it on epsilon 2, right, I'll not get epsilon 2 in general. I'll get some, some contribution also from epsilon 1. Yeah, let's call it AP. Correct?
Yeah.
Okay. Is the statement clear though? Yeah. Okay. Okay. So let's continue then. So suppose that V1 to Vn is a basis of V with respect to which T has an upper triangular matrix. Okay, so we're already assuming an upper triangular matrix. Now let lambda belonging to capital F, so lambda is some element in the field. Okay, then we can write T minus lambda I. The matrix would look something like this. Is that okay?
Yeah.
Excuse me. All right. Now we know that T minus lambda I is not invertible if and only if lambda equals one of these numbers. Right? Why is that? Because we just proved, right, that for an upper triangular matrix, invertibility is the same as the diagonal entries being non-zero.
Yeah, one of them would become 0 if lambda was equal to any one of the lambda 1 to lambda. So it would mean that it's not invertible.
Exactly. Okay, and also the other way, right? That if lambda is distinct, then it will not become 0, and not becoming 0 would imply invertibility, right? Okay, so that is good. So therefore, what do we have? We have T minus lambda I is not invertible, means its kernel is non-trivial. Right? So if a matrix is not invertible, it means
that there is at least one vector in the null space.
Exactly. Okay, so there is some
apart
vector.
From 0.
Exactly. So there is some vector V such that T minus lambda I times V gives you 0. Okay, and this is happening if and only if lambda is one of these vectors, right? One of these values, I'm saying, vectors, right? From this statement above.
Okay.
Right. Okay, so thus lambda is an eigenvalue of T if and only if lambda equals lambda 1 to lambda n. Right, because this is exactly the condition for being an eigenvalue, right? That there is some vector V not equal to 0 such that TV gives you lambda V, right?
Yeah.
So if T minus lambda is not invertible, there has to exist some non-trivial vector V such that T minus lambda I V gives you 0, right?
Yeah.
Okay. So, all right. So we have that this holds for all lambdas. So this equation holds for all lambda in lambda 1 to lambda n, right? So basically we know that these are the eigenvalues, correct? Samyak, is that okay?
Yeah, that's
Perfect. Alrighty, that was quick. So let's do one more. Oh, we finished it. Oh, nice. We finished the chapter. Is it? Or did I mess up? Let me check. Upper triangular.
Yeah, so that's the end of 5.2.
Yeah, 5C. We have 5C, don't we?
Yeah, I was just checking 5B. So
5.2.
5B is done, right? Oh, no, there's a small example actually that we should probably look at. Yeah, so let's look at this example quickly. Okay, so the example says the following. So define T to be some linear operator in F3. Okay, and Txy is given by this object. And it's asking what are the eigenvalues of this matrix T, right? So this looks like a nice question because, so first of all, we can write the, Samyak, you're with us, right?
Yeah, so what do you say? Sorry, I didn't hear you.
Yeah. So I was just saying that Yeah, we're going to look at this example, right? So here you're given some linear operator and it's asking you to find the eigenvalues. So obviously we know in general this is hard to do. So it must have some special form. And so
So it's
Txy,
upper triangular.
exactly. So Txyz, we can write it, in terms of how it would act on, say, there's a lot of noise. Emmanuel, is it, can you try muting yourself once?
Yeah, sure.
Ah. Um, okay, muted. Yeah, try again. I think it got unmuted again.
Oh, sorry.
Oh. Okay. Yeah, this is better. Yeah, Emmanuel, there was just some noise from your end, so I just thought maybe it's better. If you want to speak up, of course, feel free to unmute. Okay, there's no problem. Okay, so let's apply t on 1, 0, 0. Right. We're going to get, what do we get? We get 2, 0, 0. Right, because x is 1 and the others are 0. Right, so one can do the same exercise. You can write it for 2t 0, 1. You'll get 1, 5, 0, and then if you write it for 2t 0, 0, 1, you will get 0, 3, 8. Right, because 3z, 8z. Is that okay?
Yeah.
All right. So okay, so combining these, we can write the matrix, right? Because this gives you the first column, this gives you the second column, this gives you the third column, correct? So one can put it together, and then you have your upper triangular matrix. And now we immediately know what the values are, right? You can read them off. So it's just 2, 5, 8. Is that okay?
Yeah, that's it.
All right, perfect. And then what is it saying? Once the eigenvalues are known, then one can construct the eigenvectors by Gaussian elimination. Right? So what you do is you basically say that I want, some vector v, mv has to be the same as 2 times v. Right? So you can compute mv because you know the matrix, you know the vector. And so the vector you can just take to be ABC. As you do this, you will get 2 times ABC.
Which will be 2x plus y, comma 5y plus 3z, comma 8z.
Exactly,
So if we
exactly.
just directly use that.
Exactly. You substitute it, you will get the answer. Okay. You have to solve it, of course, but you should be able to solve. Okay. So that's just the exercise. All right. So now let's move on to section C. Let's see if we can try to make good progress with this. So now we're going to look at eigenspaces and diagonal matrices. So first, we have a definition for a diagonal matrix. It's like the name suggests. All entries are 0 except possibly along the diagonal. So these are the only things that are allowed to be non-zero. Oh shoot, yeah. So maybe Samyak, you've been with us for a while. Thank you. Let me see who else had volunteered to follow along. Wait, where is it? Oh no, it wasn't in this one. Here. Thank you, Samyak. Naneswar, is that how you say it? I'm sorry.
Hello?
Hey. Okay. Yeah, you don't have to say it's fine. Yeah, okay. I can just say yes. It's good. Okay. Right. Let's see if I can paste it somewhere
Yes.
without okay. Alrighty. So let's continue. So none is for it. Okay, so obviously every diagonal matrix is upper triangular. Oh no, I think I'll have to stop and start. Give me a second. Okay, so every diagonal matrix is upper triangular. This is obvious, right? By definition. None is for?
Yes, sir.
Hey, yeah. Feel free to keep yourself unmuted, okay? You don't have to mute yourself. It's just easier. This statement is fine, yeah? Okay. So in general, a diagonal matrix has many more zeros than an upper triangular matrix. This is completely trivial. That's fine. In an operator, sorry, if an operator has a diagonal matrix with respect to some basis, then the entries along the diagonal are precisely the eigenvalues of the operator, which we just proved, right? And it's saying that there may be a simpler proof for diagonal matrices, which we'll not worry about for now. Okay. So
Okay.
if you have a matrix that is diagonal with respect to some basis, what we proved was we said that for upper triangular matrices, if you have if a matrix is upper triangular, then the diagonal entries give you the eigenvalues. Here it's saying if it's a diagonal matrix, then obviously the statement is still true because every diagonal matrix is an upper triangular matrix. But apparently he's saying that may be an easier proof for showing this. Okay, so we'll not worry about this for now. But is the statement okay? No, yes, you know, that doesn't sound like a comforting yes.
Yes.
Okay, if it's not clear, okay, just stop. There's no, please don't hesitate. Okay, so definition 5.36 is saying the following. So it's defining an eigenspace, okay? So suppose T is some linear operator on V and lambda is some scalar. Then the eigenspace of T corresponding to lambda is denoted by this object E lambda comma T and is defined to be the null space of the operator T minus lambda identity. Okay, so the null space of this operator is called the eigenspace. Eigenspace of T corresponding to. Is that okay? Is the statement fine? Is the definition okay?
Yeah. Yes.
Okay. And intuitively, you can sort of already see why this is interesting, right? Because so remember that we had T lambda, T vector V is lambda V. This is an eigenvector of V, right? If this such a V exists for some lambda, right? So V is an eigenvector. Is an eigenvector means the following, correct? It's just almost by definition. So one can write T minus lambda V is 0, right?
Yeah.
Right. So now what it is doing is it is just considering this space and looking at the null space of this and calling this the eigenspace. Null space of this operator is being called the eigenspace of the operator T with respect to the eigenvalue lambda. Okay, and the intuition is basically just coming from here that you have TV equals lambda for all the vectors in this subspace. Is that okay?
Yes, sir.
Okay, so now this statement should be very clear. It just says, in other words, E lambda T is the set of all eigenvectors of T corresponding to lambda along with the 0.
Yes, sir.
Yeah, okay. All right. So let's continue. So first it says note. So there are a few remarks. So first it says note that for T belonging to the linear set of linear operators and lambda being a value in F, a scalar, the eigenspace E lambda T is a subspace of V. Right? Why is that? Why would it be a subspace? So let's look at the definition.
Vectors V belong to V only.
Yeah.
That's right.
Exactly, right? So what is the definition of E? It's just a null space. You could also do it directly, okay? I'm just being a little bit lazy. So it's the null space of some operator, right? And we already showed that a null space is a subspace, right? Correct?
Yes, sir.
Okay. All right. And the definitions imply that lambda is an eigenvalue of T if and only if E lambda T is not 0. Right? So if E lambda, if the null space is only the 0 vector, then it cannot obviously be an eigenvector. So is this part clear? So let's do one direction, right? So here, if lambda is an eigenvalue, right? What that would mean is that there exists V not equal to 0, such that T times V is lambda V, right? That would imply T minus lambda I is 0, right? So you have one vector in the null space which is not 0. So one direction is fine. The other direction is similar, right? So if you have T minus lambda identity, if this is not equal to 0, Oh, sorry, it's not equal to 0. Right, so then there exists some v, oh sorry, null space, right? Then there exists some v such that tv equals, sorry about that. There exists some v such that tv equals lambda v. Right, there has to be at least one other vector other than 0. So there exists some v in t minus lambda I such that, okay? Oh, in the null space. Sorry, I'm writing it a little bit wrong. I'll just write it in the null space. All right. Is everything okay so far? Can we continue?
Okay, sir.
Do you need a minute? I can pause for a few seconds if you think that would help.
Mm-hmm.
Let me know when you're ready, okay?
Yeah, okay, sir. It's fine until now.
Okay, fantastic. So let's continue. Right, so now we're looking at this example 5.3. So it says, suppose the matrix of an operator T is some linear operator with respect to some basis V1 to V3. Okay, and the matrix is as we saw in this example above, right, where we were looking at eigenvalues. Then it is clear that E8, T is span of V1. So E8, T was what? E8, T is the null space, right, of T minus 8 times identity, right, which is what? Which is the null space of the vector 8, sorry, the matrix 8, 5, this 5, 5, right, minus 8 times identity, right? So this would be 0 times whatever symmetry is alpha, so let's call it BC, right? And the null space of this vector is clearly just the 1, 0 vector, right? Nothing else goes to, that's the only vector that goes to 0, correct? Okay, and similarly for 5t and yeah, so for 5t you will have two vectors, v2 and v3, both going to 0. Right, because then the matrix would be like, I don't know, some a times 0, 0. Right, so the null space of this is what? It's spanned by the vectors v1, sorry, spanned by the vectors 0, 1, 0 and 0, 0, 1. Is that okay?
Yes, sir.
All right. Okay, for others also, if something is not clear, please let me know. We can pause and make sure that things are making sense. Okay. So now if lambda is an eigenvalue of the operator T in LV, then T restricted to E lambda T is just the operator of multiplication by lambda. Okay. So what is it saying? So remember that this E is what we were calling the eigenspace, right? Eigenspace for lambda, right? So basically it had the property that, so for all V in E of lambda T, it holds that TV equals lambda V. Right? Precisely because what was the definition? It was just the null space of T minus lambda identity, right? And lambda identity basically, so if this thing is 0, it means the vector V is such that TV equals lambda V, correct? Is that okay?
Yes, sir.
Yeah, okay, fantastic. So therefore the operator T, when you restrict it to E lambda T, so T when restricted to E lambda T, okay, and it'll also go to E lambda T, then this basically just acts as a matrix multiplication by lambda. Sorry, scalar multiplication by lambda. Is that fine? Good? Make sense? No? If it's unclear, you can take a few seconds to digest it, or you can ask a
Can you
question.
explain it once more? Story.
Yeah, sure, for sure. Okay, so So what is the definition of E? So E was called the eigenspace for lambda, right? What is eigenspace? So it was defined to be basically vectors in this null space of T minus lambda I, right? So this is the definition of, so E lambda T, right? It was defined to be the null space of T minus lambda I, correct? Who asked the question? Can you say
Yes,
a name,
sir.
please?
Suhan.
Suhan, okay. So Suhan, is the definition okay? This is just this is how we are
Yes,
defined
yes,
it. Okay.
yes,
So now, what this means, so if a vector is in the null space, right? So it means that for all vectors V in E lambda comma T, it would follow that T minus lambda I acting on V would give you 0, correct?
yes,
Right. So TV would always be lambda times V, correct?
yes, yes,
But that is all that it is saying, right? It's just saying that if you take any vector in this subspace, which is called the eigenspace for lambda, the action of this operator T, well, how would you describe the action? The action is just scalar multiplication by lambda, right? It doesn't do anything else.
yes,
Okay, so that is all the statement is saying. It's just saying if you take the operator T, right, and you restrict it to this subspace, then the action of this operator is just scalar multiplication by the scalar lambda.
got it.
Yeah, okay, perfect. So let's continue then. All right. Now, the sum of eigenspaces is a direct sum because proposition 5.38 is going to tell us that these eigenspaces are very nice. They actually form a direct sum. So let's state it more formally. So suppose V is a finite dimensional vector space and T is a linear operator on V. Okay. Suppose also that lambda 1 to lambda m are distinct eigenvalues of T. Yeah. Then when we write the sum of these subspaces, they form a direct sum. Okay, so these are subspaces, right? So each of these are subspaces. And when we write this direct sum, it forms when we write the sum, it forms a direct sum, which basically means there's a unique way of writing them in terms of vectors in these subspaces. Yeah, so recall direct sum was so U plus U2 UM is a direct sum if vectors U in U1 UM can be written uniquely where
Each J belongs to U.
exactly. Is that okay?
Yes,
Okay, so that is what it is saying. It is saying that these subspaces form a direct sum. And then furthermore, it says that the dimensions, when you add them, it would be at most the dimension of the vector space V. All right? Is the
Yes,
statement
sir.
can take a few seconds, okay? Just make sure that the statement makes sense. Excuse me. Got it. So let's see how to prove the statement. Yeah, maybe we had a few more volunteers. We can also switch volunteers now. So this is Gnaneswar, right? Thank you so much, Gnaneswar. Jayant, was it? Jayant, are you around? Or Manan, either one of you? Jayant, Manan? None of you are around? Okay. So maybe we can just cycle back. Hershey, do you want to resume?
I got lost in between, so I'm not really following right now.
No, you're supposed to tell me that was the deal. Oh man. Okay.
Sir, Jayant is there, just his mic is not working, so he'll
Poor
probably
thing.
fix it and
Okay,
try
so
to
let's stick
talk.
with Gnaneswar then. Sorry, Gnaneswar, is it okay to continue with you? I know it's been a while, but
Yeah, it's okay, sir.
okay, I'm so sorry. Yeah, okay, so let's continue then. Right, so now we are saying that we want to prove this, right? So we want to show that it's going to form a direct sum. So let's see how to do it. So to show that E1 to E lambda 1 to E lambda m is a direct sum, suppose that it is the case that U1 plus UM is 0, where each uj belongs to E lambda comma t. Okay. So suppose that there are vectors in each of these subspaces such that when you sum them, it gives you a 0. Okay. Now we are going to recall proposition 5.10, which is the following. Because 5.10 says the following, that let t be some linear operator, and suppose lambda 1 to lambda m are distinct eigenvalues of t, and lambda 1 to lambda m are corresponding eigenvectors. Okay, then lambda 1 to lambda m are linearly independent. Okay, so basically saying that as long as the eigenvalues are distinct, the corresponding eigenvectors are going to be linearly independent. Okay, this is proposition 5.10. Now I don't remember if we proved this. Maybe we did. We must have. 5.10 is before, right? We are on 5.3. So you must have proved this. Okay, I don't remember, but I'm sure we proved this then. Okay, so is the proposition clear? Distinct eigenvalues implies independent eigenvectors. Is that fine?
Yes, sir.
Okay, so from this we conclude that each of the uj's must be 0 here, right? Because if you have a sum of linearly independent vectors giving you 0, then the only way this can happen is if each vector is 0, correct? Otherwise,
Yes,
it
sir.
would become linearly dependent, right? So that's the only way this can happen. Is that okay?
Okay, sir.
So I don't know if you're following or you're just saying okay. I hope it's making sense. If something's not clear, ask. Okay. Got it. So proposition 1.44 says what? So proposition 1.44, let's see what the statement is. The statement is, suppose U1 to UM are subspaces of V. Okay. Then U1 to UM is a direct sum if and only if the only way to write 0 as a sum of U1 to UM, where each uj belongs to uj, is by taking each uj to be 0. Okay, so the statement is the following. So U1 plus UM is a direct sum. Is a direct sum if and only if the only way to write 0 as a sum of U1 to UM, where this belongs to U1, this belongs to UM, is by taking uj to be 0 for all j. Is the statement clear?
Sir, are each small user linearly independent?
Here in this statement, no, nothing is being said about linear independence. It is just said that U1 to UM is a direct sum if and only if the only way you can write the vector 0 in terms of vectors from U1 to UM is by taking all these vectors to be 0. Okay, linear independence is already there because we used it in like some previous part of the proof, but this statement itself is not relying on linear independence, right? The statement is just saying that if it is a direct sum, it must be the case that, but of course it's related, right? All of these things are related. But the statement of the proposition doesn't invoke linear independence at this point. Okay?
Okay, sir.
Okay, so that is the statement. So now going back to the proof, right? We already proved that all these u's must be 0, correct? If each uj belongs to, so think of this as capital U1, think of this as capital UM, right? So each uj belongs to capital Uj. So we just proved that the sum of these things is 0 only when all of these little u's are 0. Correct? This is what we concluded. Right? So the only way we can write 0 is if all the uj's are 0. And the proposition was saying what? The proposition was saying exactly that this must mean that ui's form a direct sum. Right? This is exactly what the statement of the proposition was.
Yes, sir.
Yeah, I can give you a few seconds to make sure that everything makes sense. So first step was we used distinct eigenvalues means linear independence. We use linear independence to argue that u1 to um all have to be 0, right? If the vector has to sum to 0. And then we used proposition 1.44, which said that if the only way to write 0 this form is when all the vectors are 0, it would mean that capital U1 to capital Um form a direct sum. Right?
Yes, sir.
Okay. All right. And then it says to show the dimension part, we note that the dimension of all of these, so you can think of these as U1 to UM, right? So the sum of their dimension is the same as dimension of the direct sums. Okay. So because essentially they are, you can think of them almost like disjoint things, right? Because direct sums are basically acting like the only common vector is essentially the 0 vector, right? So they're essentially acting as disjoint sets. So the dimensions essentially taking the dimension of the whole vector is the same as taking the dimension of each of the vectors in these spaces separately. Okay, and one can also prove this. This is I'll add this as an exercise for you to look at. Okay, so this statement is the basic idea is you're thinking of them as disjoint sets and you're taking the sizes of the disjoint sets, right? So size of disjoint sets, if you like, union over disjoint sets is the same as union over size of disjoint sets. So it's with nothing common. That is just the intuition, okay? The formal argument is here. Is the same as union over the size of sets. Is that okay? Like if you have a bunch of different sets, the total size would be you take the size of this plus the size of that plus the size of this. Of course, if there's overlaps, then it doesn't add up. Is it making sense?
Yes, sir.
Right? Okay. So that's how you get this equality. And then the last step is basically just saying that since these are subspaces, right? So you would never exceed the dimension of the space they were in to begin with. Okay. Each one of these was subspaces, right? U to UM. These are all subspaces. So if you take a direct sum of subspaces of a vector space, right, it would never, or even a sum, right, it will never exceed the dimension of the sum because you're still looking at vector space. So you will never exceed that, right? Okay, so that is the full proof for this for proposition 5.38. Okay. I'll wait for a few seconds in case something is not clear that you maybe want to ask again. And then maybe I can stop with the next definition. Okay, so let's continue then. So let's see, we do have Okay, let's see. All right, so definition 5.39 says the following. It says an operator T is called diagonalisable if the operator has a diagonal matrix with respect to some basis capital V. Okay, so diagonalisable means that you can get the matrix to a diagonal form by changing the basis. Okay, so here is a quick example of what this means. So it says define T as follows. So it's 41x, whatever this object is, and one can read the coefficients. So the coefficients of x would give you the first column, essentially. So it's 41 minus 20. Coefficients of y would give you the second column, right? Which is 740. It's just the same idea as I just said. You write with 1, 0, you write it with 0, 1, and then you see what the matrix looks like. Correct?
Yes, sir.
Okay, so this is obviously not a diagonal matrix. However, it can be made diagonal because it just says that you can use this basis. So you use the basis. So you have T acting on 1, 4. You would see it would give you 69 times 1, 4, and T acting on 7, 5 would give you 46 times 7, 5. Okay. So it shows that a priori it's not clear whether a matrix can be diagonalized, but once given a basis, it's not difficult to verify. Is that okay?
Yeah, okay, sir.
Sir, actually, in the above proof, can you read why each ui, small ui, should be 0?
In the proof above, yeah, what can we do?
Can you please repeat why each small ui must be 0?
Here? This one? Yeah. So here we used the fact that if you have distinct eigenvalues, then the corresponding eigenvectors are linearly independent.
Right. So the eigenvectors are u1 to um, right?
Exactly.
So that would mean the constant should be 0, right? Like, how are we saying that the vectors are 0?
Oh, because we're absorbing the constants, right, into the vector itself. So we're writing. So if you want to write it as normalized vectors, we haven't even talked about normalized vectors. Yeah, it's just saying that so u1 is in capital U, right? So if it is an eigenvector, you're right, you would have to write it as some alpha times, say u1 hat is say the eigenvector, which is not 0. So u1 would be alpha 1 times u1, u2 would be alpha 2 times u2 hat, if you like, and so on. Where these things are non-zero, but you're scaling them, right? It's a subspace, right? So all scalings are included in the subspace. So you're exactly right. The only way you can write it as a sum is if all the vectors are 0, or basically all the scalars multiplying the vectors are 0.
Okay. So u1 is like a scalar into some other vector, and we're saying that scalar must be 0. So we're saying u is 0.
Yeah, which is the same as saying the vector is 0, right? Because 0 times 1, 0 is a 0 vector, right? So yeah, that's what it means. It's the same thing, yeah. It's not different. Okay. Oh shoot, we are past time. I'm so sorry. Okay. Thank you so much, you guys, for joining. I hope it was clear. And yeah, see you. So later this week we don't have a class, right? It's only next week. Nobody knows.
Yeah.
Okay. Yeah, we don't have a class this week, right? On Friday?
No, we don't. No, we don't.
Okay, fantastic. Okay. All right then. So then see you next Tuesday then. Thank you so much, you guys. Goodbye. Take care.
Thank you.
Sir,
yes. I was gonna end.
Can you just explain how that absorbs like the scalars in it? We are concluding that the vectors are 0, but if they are linearly independent, then the scalars must be 0, right?
Yeah. So let me say it a bit more clearly then. Right. So what are we saying? We are saying that u1. So you have distinct eigenvalues of t, right? So we have. So suppose u1 is. So I'm going to give you a simpler example, okay, to clarify what's happening. So you have span of. By the way, the class is over, okay? So people who want to leave, feel free to leave. I'm just clarifying a question that somebody has asked. So yeah, don't feel obliged to stay. Okay, so span of so suppose u1 is span of say u1 hat. Okay, so u1 hat is a non-zero vector, right?
Yes.
And U2, right? Fantastic. And U2 is the span of U2 hat. Okay, and now suppose that you know that U1 hat and U2 hat are linearly independent. Okay, suppose you're given this. Okay. Sarka?
Yes.
Okay, so now what can you say about U1? So suppose I claim U1 plus U2 is 0, where U1 belongs to capital U1 and U2 belongs to capital U2. Okay.
Yes.
So if this is 0, what can we say? We have to conclude that, you know, U1 has to be what? It has to be some, say, let's call it C1 times U1 hat, right? Because it is in the span of U1 hat. So it can only be like a scalar times the vector. And U2 would
Okay,
be
so
what?
C1, C2 both are 0.
Exactly. So the only way you can get this is when C1, C2 are 0, right?
Okay.
That's it. Yeah. And this if C1 is 0, then the vector U1 is actually the 0 vector, right? This we already proved. So that's all we were saying.
But suppose sir, all the U1, U2, U3 are all U1 at U2 at U3 at. In that case, it wouldn't be 0, no?
Then you
Suppose all
cannot.
the vectors are eigenvectors only, basically.
Yes.
All U1, U2, U3 are eigenvectors. In that case,
Yes.
we can't say they are all 0.
Yeah, you can't sum them to 0 then. Then this equation will not be true, right?
Okay, got it. The equation.
Yeah, the equation will not hold. Yeah. So he's saying that suppose you pick vectors from these subspaces such that they sum to 0. So then it concludes that because these are just, you know, essentially scaling of linearly independent vectors, the only way you can get this to be 0 is if the vectors themselves were 0.
Okay, sir. Thank you.
Okay, of course. Okay. All right. Any other questions about any other part? Okay. Okay. If not, then thank you so much. And yeah, please do go back and take a look. Hopefully things would, things would make sense. Yeah. Goodbye. Good